Okay, let's continue from sensors and encoders in control systems. Sensors and encoders are important components used to monitor the performance and for feedback in control system. For this, let's start from the potentiometers. 6.2.1 potentiometers. Yes. A potentiometer is an electromechanical transducer. How that converts the mechanical energy into the electrical energy. The input to the device is in the form of a mechanical displacement actually. It can be linear or rotational, as you know. Applied across the fixed terminal of the potentiometer, the output voltage, which is measured across the variable terminal on ground and ground, is proportional to the input displacement. Okay, you know already potentiometer. Maybe we can show an electrical circuit for this. For example, it's a kind of configuration for the potentiometer. In here we have a rotation operation. It is represented with the theta CS or theta CT, and we get here to here ET value. This is a configuration for the potentiometer. We can mathematically express this. ET will be equal to Ks times with, of course, theta CT. What is Ks mean? Ks is proportional constant. Okay. For the turning potentiometer, the total displacement of the variable arm can be set 2 pi n. So Ks mean for the mathematically can be said as E over 2 pi n. The unit will be volt over radian, because turning operation, as you know, radian, and E is the input voltage, so it will be volt over radian. Maybe it can be another configuration as like that. We have an input voltage here. We have a potentiometer here and here. It is turning at this direction, which is represented with theta 2, in here theta 1 in this direction. We have an input source here, so we can say the difference between here and here will be ET. So for this configuration, we can say ET will be Ks times theta 1t minus theta 2t. As you see here in this configuration, we have two potentiometers connected to the parallel to each other. This arrangement allows the comparison of two remotely located shaft position. In DC motor control system, for example, in DC motor control system, potentiometers are often used for position feedback. Okay, and maybe we can write it in DC motor control systems. Potentiometers are often used for position feedback. How? In here, we can connect this input to the desired value with respect to the desired value. For this potentiometer, we can connect it to the shaft or the DC motor, and then we get the position of the motor, so we can use it in the position feedback control. How can we represent it with the block diagram? For the first configuration, we can simply represent input will be theta cs times with ks. We will get et. Maybe we can represent in time domain. What about the second configuration? We have a comparator because we have two potentiometers. One of them, theta 1t, it can be minus or plus. The other of them will be inverse of this. The second one is theta 2t. And then we have a proportional gain represented ks, and then we get the et value. Okay. Maybe we can show it on the DC motor control. We have a DC amplifier connected to the DC motor, as like that. We have a load here connecting on DC motor, and then we have a potentiometer. So we get the output value, which is represented theta L. It is load, of course. And according to the reference input, here we have a reference input, we get a difference, and we will connect it to the DC amplifier. According to this difference, plus and minus, the motor will be controlled. Let's continue from the tachometers. This is the second sensing operator, 6.2.2 tachometers. What is the tachometers? Tachometers actually a motor. A motor can be operated as a motor or generator, as you know. Tachometers for the control used as a measurement, so it will used as a generator. Okay. As you know, it is electromechanical devices, and it converts the mechanical energy into the electrical energy if we use generator mode. The device works essentially as a voltage generator with the output voltage proportional to the angular velocity. In control system, most of the tachometer used are of the DC variety, so we can say the output voltage is a DC signal. We can use it in many ways, such as velocity indicators to provide shaft speed readout, velocity feedback, speed control, or stabilization. Let's give a figure for the velocity control with the tachometer feedback. We have an input signal which is called as ER, and then we have a controller we have power amplifier for the actuating the DC motor. We have a DC motor to be controlled in the system. Maybe we have a load, and then it will connect it also a tachometer. It can be called as in the control theory also tacho generator. As you see, tachometer uses the same symbol with the motor, because the structure of the tachometer and motor is the same, minus and plus, and connected to the ground. In this point, we have a signal which gives us to the velocity of the motor, and rotation can be represented with the theta. In here we have a DC motor. So this is a typical velocity control system in which the tachometer output is compared with the reference voltage, as you see. This is the actual velocity and this is the reference value. So compared with the reference value, so the desired velocity to be achieved. The difference between the two signal, which is called as E is error, is amplified with the power amplifier after the controller. So we can drive the motor, the velocity will eventually reach the desired value. For this kind of application, the accuracy of the tachometer is highly critical, as the accuracy of the speed control depends on it. Okay, but we can use the tachometer also another application, for another application. Let's do this now. Okay, let's evaluate this figure now. As you see here, we have two measurements. One of them with the tacho generator or tachometers, and the other of them with the encoder. Encoder measure the position of the motor, and tachometer is the measure the velocity of the motor, and the velocity control in here. We have an inner loop, and the outer loop we have a position control. So for this kind of figure, we can say the main purpose to control the position, not velocity. Okay, actually in this diagram we want to control the position, but the velocity feedback is often used to improve the stability or damping of the closed loop system. So we can say this tachometer and this inner loop is used for the improve the stability or the damping of the closed loop system. For such a this kind of system, the accuracy of the tachometer is not so critical. But as given before, in here we have another configuration. In this diagram, the main purpose is the control the velocity of the motor, and we have only one measurement with the tachometer, so it is so important to accuracy of the measurements with the tachometer. Let's continue from the mathematical model of the tachometers. ETT, which is the output of the tachometer, can be given as KT times the position of the shaft dt, and it will be given as KT times omega t. Omega t, as you know, angular velocity, theta t is the position of the motor or shaft. angular velocity. Okay, what is kT? kT is a constant, tachometer constant. This value is usually given as a catalog parameter and with the unit with volts over by kilo RPM. So we can say the transfer function of the tachometer is obtained by using this differential equation. ETS divided by theta TS will be given as KTS. Okay. What about the incremental encoder? 6.2.3 incremental encoder. Okay. Incremental encoders are frequently found in modern control systems for converting linear or rotary displacement into digitally coded or pulse signals. It's important. The output of the encoder is generally given as digitally coded or pulse signals. Okay, so we can say the output will be digital, not analog. So the encoders that output a digital signal are also known as absolute encoders. Okay, we can use it in modern control system. The output of an encoder is generally digitally coded or pulse signal. For example, in the datasheet, you can give some knowledge about the encoder. It gives 100 pulse for per RPM, for example. Or in the datasheet you can see it is produced or 500 pulse produced for each per cycle, for example. Okay. Incremental encoder operated as like that. Arkadaşlar bu da incremental encoder da şu şekilde çalışıyor. Her bir dönüşte arkadaşlar for each turn produce 500 pulse, for example. We can find the pulse, the number of the pulses in the datasheet related to the encoder. Let's continue from the DC motors in control systems.